All right, so the rest of today's lesson is going to be kind of a hodgepodge of information. And it's talking about how reactions actually occur and what drives reactions to occur, what causes them to occur, and how can we manipulate how easily or how fast a reaction will actually happen. Right? So kinetics is the study of reaction rates. So it's basically a reaction rate tells us how fast or how slow a reaction is going to occur. Okay? Reactions occur because molecules or atoms with particles in solution collide with each other. Right? That's the only way a reaction can occur. And the more often they collide, the faster the reaction goes. And remember, all reactions require energy, E, to make them occur. And that's called the activation energy. That's the energy that is required to start a reaction. Sometimes it's talked about as being the barrier for the reaction. Okay. Back in Unit 5, we talked about activation energy briefly. I drew those graphs. We're going to see on the next slide. I drew those graphs that show you the energy profile for a reaction. Okay. These graphs. There we go. So the left one is an exothermic reaction. It is exothermic because we're ending at a lower energy state than we are starting at. We have an overall decrease in energy. So energy is being released. But notice how we still have to put energy in. We still have this activation energy, that barrier. So energy goes in, and then we get energy back out. Okay? If the energy we get out is greater than the energy we put in, then it's exothermic. Endothermic still has that activation energy, and we're still getting energy back out, but we're getting out less than we put in. And notice how we have an overall increase in energy. So it's endothermic. It's increasing, it's adding, it's absorbing energy. Okay. Make sure you are familiar with these graphs. Okay. All right, you have nothing to write from here. So, there are 4 ways to make a reaction go faster. 4 ways. The first way is to increase the temperature of the reactants. Okay, if you heat it up. Remember, there's a direct relationship between temperature and kinetic energy. Ke is kinetic energy. There's a direct relationship. So that means that the higher the temperature, the more kinetic energy the particles have, and therefore the faster they will move, leading to more collisions. Okay. We can also increase surface area. There's surface area of the reactants. If you increase surface area of the reactants, you can break them down into smaller parts. That means that there's more sites along the reactant molecules to actually collide, which would lead to more collisions, right? And therefore, the reaction is going to occur faster. So an example is a large chunk of copper. It's going to react slower than if we broke it down into smaller pieces. You could also think about it this way. If you take like a sugar cube, a cube of sugar, and you drop it in water, it's going to take a lot longer to dissolve versus if you crushed it up or granulated it. Third way is to increase concentration of the reactants. We're going to see this a lot during this unit. If you see these brackets, that means concentration of the substance that you might have written inside the brackets. Okay? So brackets mean concentration. And when you have a higher concentration, it means that there are more moles of that substance available to react. So more particles, more collisions. Okay? An example is copper is going to react faster with 6 molar acid than in 0.1 molar. And then the fourth way is to add a catalyst. Okay? A catalyst speeds up the reaction by lowering the activation energy. So that barrier, the amount of energy it has to gain is lower, so it's going to occur faster. You've probably heard about catalysts back in biology when you talked about enzymes and substrates. An enzyme is a biological catalyst. Okay. It works slightly different from chemical catalysts because an an enzyme, when it binds to the substrate, it actually changes the orientation of the molecule and the shape of it. Whereas in chemistry, it works a little bit differently. But you don't need to worry about the differences between biological and chemical catalysts, just an FYI. That was just a little aside. Okay? Everyone good here? All right. So in talking about the drive behind a reaction, there are a couple things. One of them is the amount of energy being added or removed from the reaction, so the heat. So that exothermic versus endothermic. Reactions that are exothermic are more favorable, though that does not mean that endothermic reactions will not occur. They're just less favorable. Okay. Another factor for what drives a reaction is this concept called entropy. Entropy. Entropy is a fancy word to describe the disorder or chaos of the reaction. Okay. One of the laws of thermodynamics states that the entropy of the universe is always increasing. The universe likes disorder. It likes randomness. Right? Think about your bedroom at home. What happens to it over time?
Sleep in it.
Okay, yes, you sleep in it. It gets dirty, it gets messy, it gets disorganized, unless you put forth effort to keep it organized, right? But it just naturally tends to get disordered and cluttered. It gets dusty, you might have to vacuum the carpet, your hair gets on it, whatever, okay? So your room over time at home gets disordered. And then you have to put forth effort to keep it ordered, stuff like that. Think about this classroom. Over time, just throughout the course of the day, the desks start to move a little bit. The chairs don't get pushed in all the way, stuff like that. Your backpack gets cluttered. I've seen some really awful backpacks where it gives me so much anxiety looking in there. Okay? So that's what entropy is. All right, so a few rules. The entropy of a gas is going to be greater than the entropy of a solid or liquid. The more chances for motion of the particles, the higher the entropy. Also, entropy increases when the substance is divided into parts. So, a couple examples here. If I take that sugar cube and I grind it up, I'm increasing the surface area, so I'm dividing it into parts. Or if I take sodium chloride and I dissolve it in water, it's breaking down into parts. It's being divided. Entropy is increasing. And then entropy also increases when temperature increases. So the more motion of the particles, the more entropy it has. Okay? So let's do a few examples. So we have these 4 things where each one you're going to choose which one of those systems has a higher entropy. And when you get to letter C, just an FYI, room temperature is about 25 degrees Celsius. So why don't you guys take a couple minutes to go through these examples with your pods, and then we'll go over them as a group. So, which one's going to have a higher entropy? A new pack of playing cards or playing cards in use? Playing cards in use. And why is that? Yeah, more spread out. Or have you ever opened a new pack of playing cards?
Yeah.
Describe them to me.
They're like sticky together and
Okay, that and
all of like the keys and keys and everything are like together.
It's organized by suit.
Yeah, it's like
When you open a new pack of playing cards, they're all organized by suit. So you have all your diamonds together, all your hearts, all your clubs, all your spades, and like your jokers on the end, and then there's the couple like random cards that like are advertisement stuff. So they're ordered in a very specific pattern. Once you start using them, that pattern and that order goes away and they become more disordered. All right, sugar cube dissolved in water or just the cube of sugar? Dissolved in water. You're dividing it down into parts, okay? A cup of water at room temperature or at 50 degrees? 50 degrees. Higher temperature, higher entropy. And then a gram of a salt 1 gram of salt crystal or a gram of powdered salt? Yes, sorry, I was thinking this was lower entropy for a moment. Yes, a gram of powdered salt, more surface area, higher entropy. All right? That's it for entropy. We're going to move on to equilibrium, which is what your homework is based on. So, chemical equilibrium. There are a couple definitions of chemical equilibrium. This is a state when the, what does this mean? What do these brackets mean? Concentration so when the concentrations of all substances in the reaction remain constant. Not necessarily equal, but when they are no longer changing. Up until this point, we have learned everything in chemistry under the assumption that when you react things together, they completely form the products and we have no reactants left over. In Unit 7, we learned a little bit about limiting and excess reactants, how you can have one of the reactants left over, but then the other one will still get used up. In reality, a lot of reactions occur in both directions, which is why we're doing this reversible arrow now, okay? Because in reality, a lot of those reactions don't go completely to completion, which is what we call that. So, for example, here we have water and carbon monoxide reacting to form hydrogen gas and carbon dioxide, but once some of the hydrogen gas and carbon dioxide form, they will react together, forming back the reactants. So it kind of will go back and forth until their concentrations are no longer changing. Right? So like I said, that reverse arrow indicates that the reaction can occur in either direction until that equilibrium is achieved. All right, no net changes are visible at equilibrium, but on the molecular level, the reaction is still occurring, and no change in the concentration will occur once the equilibrium has been established. Okay? So this diagram, you have this in your notes. This is showing the water and carbon monoxide reaction. So notice how we're starting off at the beginning of the reaction. At time 0, all we have are the reactants. But as over time, they're going to decrease as they form products. Okay? And the products start off at 0, and they're going to increase over time. And eventually, there will come a point when their concentrations kind of level out. Okay? But notice how the reactants did not completely go away. There's still some there. So this was our water and our carbon monoxide, and then our products were hydrogen gas and carbon dioxide. Okay? And it has written in words here exactly what I just said. Another definition of equilibrium. So equilibrium is when the concentrations are constant, not necessarily equal. I know equilibrium has that equal word in there. It makes you think that that's the thing that has to be equal, but it's actually something else that's equal. But at equilibrium, the concentrations of all the substances are no longer changing. What is equal is the rate of the forward reaction and the rate of the reverse reaction. So the reactions are occurring at the same rates, okay, same speed. Okay? So that's our second definition. Or two different ways to basically say the same thing. All right, so with equilibrium, what we're going to do is write something called an equilibrium expression, which is what your homework is on. And it's going to be based on the balanced chemical equation. So you need to write a balanced chemical equation in order to write the equilibrium expression. So that stuff's not going away. And then you're going to take the products, put the substances in brackets to signify what? Concentration. And I meant to say this before, but that's concentration in molarity, moles per liter. So you're going to take the substances on the product side, put them in brackets, raise them to their coefficient as a power. So if there's a coefficient of 2, you're going to square the concentration. If there's a coefficient of 4, you're going to, not quadruple, but raise it to the 4th power. Okay? And then divided by the reactants, same thing. Concentrations raised to the power of their coefficient. But most important, Only aqueous and gas substances go in the equilibrium expression. Okay, so if there's a solid or a liquid, you're just going to leave it out. You can put it in as a 1 if you want to, but normally we just completely eliminate it. It's not a 0 though, it's a 1. Okay. Before we get into some practice problems with this, eventually where we're going with this is we're going to actually solve for this equilibrium constant, this K value. Okay? And what K means is when it's a larger K value, it means that it favors the products. That is when K is greater than 1. So 1 is the cutoff. When it's greater than 1, that means that the products are favored, meaning that there's going to be more products at equilibrium than reactants. When it's a small K value, so less than 1, that means that the reactants are favored, more reactants than products. When it is 1, that means both sides are equally favored, and that's a case that I've never seen. And then there's 2 definitions here. Homogeneous equilibria just means that all the substances are in the same state of matter. Heterogeneous means that there's multiple states of matter in the reaction. Okay, so let's look at some examples. So we're just going to write the equilibrium expression. We're not going to plug in numbers yet. We'll get to that after we go through just writing the expressions. So we have sulfur dioxide reacts with oxygen gas to form sulfur trioxide. And we're told that all of these are gases. Okay? So let's write our reaction. What are our reactants? Sulfur dioxide and oxygen. How do I write sulfur dioxide? SO2, and that's a gas. And that's reacting with O2, which is also a gas. Bless you. And we're going to use that equilibrium arrow, that reversible one, to show that the reaction can occur in either direction. What's our product? SO3, which is a gas. So now what do we need to do with this reaction? Balance it. So what are our coefficients when this is balanced? 2, 1, 2. All right, so now we're ready to write the equilibrium expression. On the top are the products. It's always products over reactants. So the top, we only have one product, that's SO3. So I'm going to put SO3 in brackets and raise it to what power? A 2, because that's its coefficient. And then the bottom is going to be the reactants raised to their coefficients. So we're going to have SO2 squared times O2 to the first. Notice that on the bottom I multiplied the 2 reactants. I did not add them. No addition or subtraction signs in an equilibrium expression. Only multiplication and division. But that's it. That's the whole expression. That's what your homework is. And actually your homework's even easier because I gave you the balanced chemical equations already. Okay? Later, after we get through the next 2 problems, then we'll actually plug in numbers and solve for a K value. Questions so far? Okay, let's do the next one. Sulfur trioxide gas is bubbled through water to form sulfuric acid solution. So what is one of my reactants? Which is SO3. What state of matter is that? Gas, because it told me right here. What's it reacting with? Water, which is H2O. State of matter? Liquid. Equilibrium arrow. And what is it making? Sulfuric acid. Ooh, what's the formula for sulfuric acid?
H2SO4.
Good job. H2SO4. Because it was sulfate, because it comes from sulfuric. There's no hydro in front, so it's 8. H2SO4. Make sure you go back and review that Unit 4 stuff. What state of matter? Aqueous, because it's a solution. Bless you. My goodness. All right. What are the two states of matter that we're allowed to put in the equilibrium expression? Gas and aqueous. Gas and aqueous. Liquids and solids don't go in the expression. So, for this one, my top is going to... Oh, wait, sorry. I got ahead of myself. What do we need to do with this reaction? Balance it. And this one's already balanced. All right, so on the top of my expression is going to be my product, H2SO4. And that's raised to the first power. And then the bottom is going to be what? SO3. What do we do with the water? You can put it as a 1 or completely ignore it. Either one. Okay? The actual states of matter, you don't have to write in the expression. I mean, I guess you could. It's just going to take up more space.
Do you only include aqueous and gases?
Correct. Only aqueous and gas. All right. Last example, and then we'll get into plugging in numbers. Solid copper 2 sulfate pentahydrate is intensely heated. You may recall doing this back in Unit 6 when we did that hydrate lab, where we took the blue crystal and we put it in an evaporating dish and then we heated it, and then it turned white because we were driving off the water. Okay, we actually did this reaction. So what's the formula for copper 2 sulfate pentahydrate? CuSO4. That's the copper 2 sulfate. What does pentahydrate mean? 5 H2Os that are chemically attached to that copper 2 sulfate matrix. And what state of matter is that? Solid. Now, when we heated this, what we did is we were breaking the bonds of the waters to that copper 2 sulfate. We were breaking it here. And that white solid that we produced was just solid CuSO4 without the waters. And then where did the waters go? They evaporated. And well, when we decomposed it, the water came off as a gas. So what do we need to do with this reaction? Balance it, always. What do you get when this is balanced? 115. We just need a 5 in front of the H2O. So now we're ready to write the expression. What's the only types of substances allowed in the equilibrium expression? Gas and aqueous. So what's the only thing that's going to go in this expression? The water. So it's going to be H2O raised to what power? 5. And you can write over 1 if you really wanted to, but it's not necessary. Okay? All right, so now we're going to do just a couple more. We're just going to go through the bottom of the next page. We're just going to do page 20, and then we'll be done. We're going to actually plug in numbers and talk about the equilibrium constant, the value, the magnitude of it. It's going to be the same thing. We're going to have to write the equilibrium expression and then just go one step further. Plug in the numbers that I've given you. So we have this reaction, which might look familiar because it was number 1 from the previous page. We need to write the equilibrium expression of that reaction, which we already did, and it was SO3 squared over SO2 squared times O2. And now I ran, I did not run. We have data on 2 different experiments for this same reaction. And the equilibrium concentrations of those substances were recorded for each experiment. Okay? So we're just going to plug these numbers into the expression to solve for the K value. So I'm going to set up both problems once you start calculating. So for experiment 1, we're going to have K equals SO3 is 0.260. We're going to have to square that. SO2 is 0.590. We're going to have to square that times 0.045 raised to the first power. Make sure you're multiplying and dividing properly. And then for the second one, the top is going to be 3.50 squared over 1.50 squared times 1.25. See, I'm just pulling the numbers from the chart. So start calculating them. So what did you guys get? Has anyone gotten the experiment 1 K value? You did something wrong. 4.32? That sounds right. So make sure that, like, redo the, if you didn't get 4.32, redo your calculation, try to find where your error is, make sure you can get 4.32. I'll talk about that in a moment. What did you get for experiment 2?
4.35. 4.36.
Yeah.
Yeah. Oh.
4.36. Okay. Is there a huge difference between those two values? No. It might have just been, a slight rounding error earlier on, or maybe a slight measurement error with one of these concentrations, but they're virtually the same. So the conclusion is that the equilibrium constant is a constant for that temperature. If we change temperature, it actually changes the equilibrium constant, but you don't need to worry about how it changes it. Okay? So the equilibrium constant is a constant. What does this magnitude of K tell us about the reaction? How would you describe this K value in relation to 1? It's greater than 1. Therefore, which side of the reaction is favored? Which side? The reactants or the products? When K is greater than 1? When K is greater than 1, the products are favored. That's what we wrote on that previous page. It means that we're going to have more products than we do reactants in general. Okay? More products than reactants. Now, somebody asked me about units for K value. We technically could calculate the units. All of this was molarity, so we'd have molarity squared over molarity to the third, and it'd be 1 over molarity. But the units are going to change for every reaction. So because they're variable from reaction to reaction, we do not report units on K values. Okay? Makes it nice and easy. So you just leave them as naked numbers, and that's okay. All right, last example. So we have this one. We have nitrogen and hydrogen gases mixed to form ammonia at 298. The concentrations of each gas are measured at equilibrium and are listed here. You're going to go through the whole thing. You're going to write the reaction, balance it, write the equilibrium expression, and plug in. If you are having issues writing the formulas, they're like literally given right here, and they're all gases. Okay? So go through this problem. Write the reaction and calculate the equilibrium constant. So what is this reaction written out? Not necessarily balanced, but what are the reactants? N2 and H2, and both of them are gases. And what is my product? NH3, which is also a gas. So you should have balanced that reaction. When you balanced it, you should get 1, 3, 2 as your coefficients. Come on, pen. There we go. 1, 3, 2. So when we write the equilibrium expression, what goes on the top? Which is the ammonia, NH3. And we're going to have to square it. And then on the bottom, we're going to have N2 times H2 cubed. So now we're going to plug in the numbers. NH3 is 0.400. We're going to have to square that. Divided by N2, which is 0.200 times 1.20 cubed. So when you do that math, you should get 0.463. And remember, we don't report units on K values. If you don't get 0.463, make sure you're do like the extra parentheses around the bottom, or do the entire bottom separately, or something like that. Make sure you're not multiplying when you're supposed to be dividing. So what does this K value's magnitude tell us about the reaction? The reactants are favored. Since K is less than 1, reactants are favored. Okay? Your homework, the worksheet that you got today, based on this stuff, is just getting up through the expression part. Okay, and like I said before, it's actually even easier because I already gave you the reaction. It's just practicing writing the expression. Okay? Because I feel like if you can write the expression, you can plug in numbers. Where you might be having issues with plugging in the numbers is literally typing them into your calculator. And that's just going to take practice. Okay? So that is it for today. Let me stop this video.